Oh, that's nice. Okay, so read the question. Read the question, pause. Correct answer is 1. Positive is more outgoing than going in. Read the question, pause. Correct answer is 4. You're looking at the component of the electric field. So this is the side view. Looking at the component of the electric field that is perpendicular to the area. So that's 30 degrees. I want to find the cosine of this. I want to find the component that's perpendicular to that. Okay, so I'm going to do a cosine of that. And it's negative because it's going in. Read the question, pause. So, correct answer. So, flux is equal to the component of electric field that is perpendicular to the area. So, here's your area. Here's your electric field. And here's your 20 degrees. This is also 20 degrees. I want the component that is perpendicular. So I want that. That is perpendicular. So I mean, do sine of 20 or cosine of 70. See. Have a conversation. Tell them why.
No. No, that's only tables were more extreme for A, but looking at it,
Three-dimensional
every
shapes.
line intersecting B is intersecting with the same angle as A. And
If these are right? It's not zero.
Okay, correct answer is A. There are more lines per area. Considering, like, assuming these have the same area, there's more lines going through this. There's a stronger electric field closer to the charge. Good with that? Tell your neighbor.
The three-dimensional ones. Yeah, I have the ones like this right here. For this one, there's stuff going in. For this one, there's stuff going out. But like, if it's just like this, like it's doing.
Correct answer is Correct answer is C. Okay, here's a sneaky way to do it. You know that the electric field lines going in to that object are equal to the electric fields going out. Like there is no charge in there, so therefore the net flux has to be 0. So whatever's going out has to go in. That's a backdoor approach. Not really a huge fan of that. Here's the straight up why they're equal. This area A is looking at it from this point of view. This is the component of the area of B that is perpendicular to the electric field. Okay, right now, if you're looking at this, there's if you want to say like wind or light rays going through here, as much as this is as much wind as possible, much flux, wind flux. Okay, as I do this, the amount of wind flux is decreasing. The cross-sectional area of this is less. Does that make sense? This, no flux. There's no, it's not going through the area. Does that make sense? So here, if you can, I'll do it like this. This, if you can look at this rectangle with the height of that, does that make sense? That's the area. That's the perpendicular. You could say a cross-sectional area, I guess you could. Good with that? Okay. It's helpful if you employ Gauss's law on this one. Tell your neighbor.
Within C is 0, and D has no charges inside of it. So according to Gauss's law, the answer C on the surface, the answer C. What's there?
Okay, correct answer is E. Educated elephants. All right. So whatever's going out comes back in. Whatever goes out whatever goes in comes out. Definitively, how we know this is that the enclosed charge in the gold is nothing, so the flux is 0. Enclosed charge in the purple is nothing, so the total flux is 0. Now, let me throw out this misconception. I am not saying that the electric field is 0. That is not what I'm saying. Okay, the flux of this enclosed area is 0 because whatever went out came back in. So the positive flux is negated by the negative flux. Okay, Josiah.
So Is electric flux like the change in electric field?
No, it is not. It is the quantity, it's a measurement, it's a mathematical calculated measurement that we've synthesized to help quantify, describe what goes on to the electric, or like, yeah, it's like, it's just the electric field times the area that it goes through. So it's like we've concocted this measurement to help us describe stuff.
Just its own way.
Yep. Tell your neighbor.
Between all of them? I assume it's That's what I did.
You're right. Yeah, I think I know.
Correct answer is B. There's more going in than going out. 20 going in, cancel out with 20 going out. 15 going in, it's canceled with 15 going out. 15 going in is, more going in than coming out. There's 5 more going in than coming out. Okay. Yes, yes, yes. Good. Okay. Tell your neighbor.
But he has a bigger charge. Yeah.
Correct answer is B. Okay. Using Gauss's law, there's more enclosed charge here. Therefore, there's going to be twice as much flux. There's twice as much charge enclosed. Good with that? Tell your neighbor. Correct answer is C. Okay, it's all about how much charge. It's not about where the charge is located or how big or small it is. In terms of the volume, it's just about how much charge. Have a conversation. Correct answer is dos. Everybody go with that? Okay, it's all about the charge enclosed. I don't care about the shape. Okay. La la. Converse.
I solved I solved the gray one, and the green it's in mystery class. Do you know that Rubik's the root now?
Correct answer is
And there's like and it's harder because you can't just
correct answer is B. Get to that. Next question. Have a conversation. Correct answer is everybody good with crazy cats? Ugh. All right, so Gauss's law. Here we go. The enclosed surface, regardless of the shape, it just needs to be enclosed. It needs to be a bubble. Does not have to be spherical. It just needs to be enclosed. And so here we recognize that the charge is on the outside of a conductor. So when we do a Gaussian surface on the inside of this, the charge enclosed is equal to 0. There's still area, so that must mean that the electric field on the inside of a conductor is equal to 0. One application. Good with that? All right, so if we looked at a point charge or a spherical conductor that's charged, we're going to condense that down to point charge at the center. And so the electric field at this location or this location is the same. Okay, so we can pull out the electric field because it's constant at that distance away. Charge enclosed is Q and epsilon naught. This, our Gaussian surface, is going to be a sphere. Sphere, the area of that, without doing calculus, just memorizing stuff from geometry, is 4 pi r squared. Okay. Equals Q, epsilon naught. Solving for that, you have 1 over 4 pi epsilon naught Q over R squared. Crazy. Hopefully that's in your brain already. Point charge. You'll do this a bazillion times. Sure, write it down. Okay, so regardless if we do it this far away or not, the flux stays the same, but the electric field, I mean, it should, yeah. Good with that? Okay, point charge. All right, so on a conductor, this is probably as far as we're going to get. On a conductor, inside the conductor, you have 0 electric field. On the outside, for a sphere, it behaves like a point charge. Okay. Nothing new, it's just a different way to look at it. And we are going to, how much time do I have? 5 minutes. Well, we'll see what we can do. All right, so what happens if we have an insulator that is uniformly charged throughout its volume? 14. Yeah, we got some time. All right, so is everybody okay with when I do this, I just get the same thing as I had as just a point charge on the outside? Okay, all the charge is in the Gaussian surface. Okay, but now let's go into that insulator and develop an expression for the electric field at a certain distance within the insulator. So this has very similar feel to going into a planet, finding the gravitational field in a planet. Okay, so we have our expression for charge density. So we have charge over volume, which is equal to charge over 4/3 pi r cubed, and this is Q on the inside, so the purple part, 4/3 pi lowercase r cubed. So I'm looking at the charge in the purple part, in the Gaussian surface. That's what I care about. Okay, and that is that. Okay, so I have E is equal to 4 pi lowercase r squared, because I'm looking at the surface area of the Gaussian surface. And then here I have 4/3 pi lowercase r cubed over 4/3 pi uppercase cubed times Q over epsilon naught. And the pi's 4/3 go away. Oh, yeah. And then I bring that over here, and I get an expression that says 1/4 pi epsilon naught. This r cancels out those, and I'm left with r cubed on the bottom, q's on top, with an r out there. Woo! Made it. Yeah, buddy. Ooh-la-la. Yes, right? I think I got it. Just
And that big Q is the overall charge of the insulator?
Yep. Good with that. And so what we find is on the inside, it's linear, and then outside it behaves like a point charge. I'll work on your free response. What do they do in a week? Mm-hmm.
What if you put it on Tuesday instead? That would be you high five. That way, when we came back from the weekend and we forgot to do it, we were like, guess what's due tomorrow?
Or I can make it due on Friday.
No.
And then you wouldn't have that problem at all. Good with that.